Tonight, we're going to explore a rock that didn't have a name 8 days ago. Take a moment with that sentence. 8 days ago, this object did not exist in any human record. It had no catalogue entry, no provisional designation, no orbital calculation attached to its name, because it had no name. The telescopes that spend every clear night scanning the sky for exactly this kind of object had not yet caught it. The software systems running automated comparisons of millions of star positions, looking for the one faint dot that moved between frames, had not yet flagged it. As far as any human instrument was concerned, this rock simply was not there. And then, on May 10th, 2026, at 4:46 in the morning Universal Time it was. A survey telescope in the Santa Catalina Mountains of Arizona caught something. A point of light, extremely faint, that had shifted its position against the fixed background of stars. By itself, that means nothing. There are millions of such points. But this one moved again on the next exposure, and again on the one after that, in a pattern consistent with an object relatively close to Earth and moving fast. The software flagged it. A human reviewed it. More observatories were alerted. More measurements were taken. Within hours, enough position measurements had accumulated to calculate an orbit. And when the orbit came back, the result was this. In 8 days, this object was going to pass between Earth and the Moon, not near the Moon, inside the Moon's orbit, at roughly a quarter of the distance between us. It received a name, 2026 JH2. Now let's sit with what that distance actually means, because the number by itself, approximately 90,000 kilometers at closest approach, doesn't carry the weight it deserves without some context. The Moon, on an average day, sits about 385,000 kilometers away, so this rock, on its closest pass, came in at roughly a quarter of that. But here's where the geometry gets genuinely interesting. The ring of geostationary satellites, the ones we depend on for communications, for weather forecasting, for the GPS signals that now underpin almost everything from aviation to agriculture. Those satellites orbit at approximately 36,000 kilometers. 2026. JH2 passed outside that ring. Our satellite infrastructure was never at risk, but the geometry remained striking. This rock flew through the gap between the instruments we have placed in orbit and the Moon that has circled us for 4.5 billion years. In astronomical terms, it threaded a needle, and it was not alone. In the same stretch of time, approximately 8 separate asteroids passed inside the distance between Earth and the Moon. Most of them were also recently discovered. Most of them carried similar designations because they were all found close to their closest approach. 8 objects in a single week, passing through what astronomers call the Earth-Moon distance, which is itself a region that most objects in the solar system never visit. Tonight, we are going to explore what that means, not just for this particular rock, which is already gone, already accelerating back toward the outer reaches of its orbit, already too faint for most telescopes to follow, but for what 2026 JH2 reveals about the neighborhood we live in, the limits of the systems we have built to watch it, and the strange, quiet reality that most of what moves through our corner of the solar system remains invisible to us until the moment it is almost upon us. This is a story about a rock, but it is also a story about looking, about what we can see and what we cannot, about the gap between the universe we imagine ourselves to be watching and the universe that is actually out there, moving on its own schedule, indifferent to whether we happen to be paying attention. Settle in. There is a mountain range in southern Arizona called the Santa Catalinas. If you drive north out of Tucson on a clear night, you can see the range rising against the sky, dark and enormous. The city's light pooling in the basin behind you and thinning as the road climbs. At roughly 9,000 feet, near the summit, there is a complex of observatory domes, white structures, rounded, pointing at the sky. During the day, they are unremarkable. At night, when the domes open and the telescopes inside begin their work, they become something else entirely. This is the Mount Lemmon survey, one of the primary workhorses of what planetary scientists call the Catalina Sky Survey, a program funded by NASA's Planetary Defense Coordination Office and dedicated to a single purpose: finding near-Earth objects before they find us. The main instrument here is a 60-inch reflector telescope, which sounds impressive until you understand that by modern astronomical standards, it is a modest instrument. It was not built to image distant galaxies or resolve the surfaces of stars. It was built to scan. Night after night, clear sky permitting, it photographs wide patches of sky in rapid sequence, returning to the same patches minutes later, then minutes after that, building up a sequence of exposures that the survey's software can compare frame by frame. The logic of the search is straightforward, even if the execution is anything but. Stars, from the perspective of any Earth-based telescope, do not move. They are so distant that even the fastest of them, crossing the galaxy at hundreds of kilometers per second, appear absolutely fixed over timescales of months or years. An object in the inner solar system, by contrast, is close enough that its motion is real and visible. A near-Earth asteroid moving across the sky will shift its position between exposures taken minutes apart. The software is looking for exactly that shift. It compares the position of every point of light in the first image against the same point in the second and third and fourth, flagging anything that appears to have moved. In practice, this produces an enormous number of candidates. Cosmic rays striking the detector look like moving points. Satellite trails, of which there are now thousands every night, can mimic the signature of a fast-moving object. Artifacts in the image data, hot pixels, reflections, edge effects, all of them can fool an automated system if the system is not sophisticated enough to reject them. The Catalina Sky Survey's software has been refined over decades of operational experience to handle exactly this noise. But the fundamental challenge remains. The universe is not quiet, and the things you are looking for are extraordinarily faint. The faintness is the key problem. A near-Earth asteroid does not glow. It does not emit light. What the telescope sees is reflected sunlight, and the amount of sunlight a rock reflects depends on two things: how big it is and how reflective its surface is. Astronomers use a number called absolute magnitude to describe how bright an object would appear at a standardized distance, and this number is the primary handle-on size for a newly discovered object. A rock with a high absolute magnitude number is faint. 2026. JH2 had an absolute magnitude estimated between 26.1 and 27.3, depending on which measurements you use. That is extremely faint. Fainter than anything the human eye could register under any circumstances. Fainter than most amateur telescopes could detect even under ideal conditions. Detectable by the Mount Lemmon survey's 60-inch reflector, but only barely, and only once the object had already come close enough to brighten slightly against the background sky. This is the fundamental reality that shapes everything else about the story of 2026, JH2. The reason nobody knew about this rock 8 days before it arrived is not that the search programs are poorly funded, or that the telescopes are inadequate, or that someone made a mistake. The reason is physics. A rock this size, this faint, moving on an orbit that brought it in from the outer solar system, simply was not detectable by any ground-based instrument until it had already closed most of the distance between itself and Earth. The detection happened at the last reasonable moment, because the last reasonable moment is the only moment when detection was possible. At 4:46 Universal Time on May 10th, the Mount Lemmon survey's software flagged a candidate, a faint point of light that had shifted between exposures. The flag was reviewed, the candidate was found credible, and a report was submitted to the Minor Planet Center in Cambridge, Massachusetts, which serves as the global clearinghouse for new solar system object discoveries. The Minor Planet Center received the report and circulated it to other observatories. This is standard procedure. A single observatory's measurements are good, but not sufficient to calculate a reliable orbit. You need multiple observations from different locations, taken at different times, to build up a picture of where the object has been, and therefore where it is going. Over the following hours and days, additional observatories across the United States picked up 2026 JH2 and contributed their own position measurements. The Farpoint Observatory in Waban State County in Kansas was among them. More measurements came in, more positions, more data points for the orbital calculation software to work with. Orbital mechanics, at its core, is a solved problem. Given enough position measurements of sufficient precision, taken over a sufficient span of time, the equations of motion under gravity will yield a unique solution, a single orbit that fits all the observations. The catch is that the confidence in the solution grows with the number of observations and the length of time over which they are spread. An object observed for 8 days has what astronomers call a short arc, and a short arc means the orbital solution carries real uncertainty. The longer you watch something, the better you know where it has been, and the better you know where it has been, the more precisely you can say where it will go. For 2026 JH2, the orbital solution came together quickly because the object was moving fast and the position measurements were accumulating rapidly. Within roughly 2 days of the initial discovery, enough data existed to establish the key facts. The object was an Apollo-class near-Earth asteroid, meaning its orbit around the Sun crossed Earth's orbit. It was moving at approximately 9.21 kilometers per second relative to Earth at closest approach. And on May 18, 2026, at 21:23 Universal Time, it was going to reach its closest point to Earth at approximately 90,000 kilometers, or about 0.24 times the average Earth-Moon distance. The object was given a provisional designation, 2026 JH2, the year of discovery, followed by letters indicating which half-month of that year the discovery occurred in, and the sequential order within that half-month. A naming system designed for volume, because the Minor Planet Center processes thousands of new discoveries each year, and most of them never accumulate enough observations to earn a permanent name. 2026, JH2 joined the catalogue, its orbital solution filed, its close approach confirmed, and then, because it posed no impact risk, the observatories moved on to the next candidate in the queue. There is something worth pausing over here. The process that produced the discovery of 2026 JH2, from the first flagged exposure at Mount Lemmon to the confirmed orbital solution and close approach data, took roughly 2 days. The close approach itself was 8 days away, which means that for 6 of those 8 days, the object was known. It had a name. Its path was calculated. The people whose job it is to watch this part of the sky knew it was coming. But for the years before May 10th, 2026, which is to say for the entire history of this rock's existence as an object in the solar system, it was unknown. It had been circling the Sun on its 3.7-year orbit since long before any human existed, long before any telescope existed, long before Earth itself had the atmosphere and oceans and continents we know today. It passed through the inner solar system on previous orbits, perhaps close to Earth on other occasions, perhaps not, and nobody was watching or could have been watching because the instruments did not exist, and even if they had existed, the rock would have been too faint to see. What changed in those 8 days was not the rock. The rock was the same rock it had always been, following the same orbit it had always followed. What changed was that the geometry of the solar system briefly put this particular object in a position where it was close enough and bright enough to cross the detection threshold of a survey telescope on a mountain in Arizona. For 1 week, this billion-year-old rock became knowable, and the system, working exactly as designed, caught it. This is worth sitting with, because it changes the way you think about the event. The question most people ask when they hear about a close asteroid flyby is some version of, why didn't we know sooner? The answer is not that we weren't paying attention. The Catalina Sky Survey runs every clear night. Mount Lemon's 60-inch reflector photographs millions of sky positions per year. The Minor Planet Center processes every report. The systems are running continuously without pause. The answer is that there are hard physical limits on what those systems can detect, and an object in the size range of 2026 JH2, roughly 16 to 35 meters across, sits well below the detection horizon for most of its orbit. It becomes visible for a brief window, a window measured in days rather than weeks or months, and if the survey telescope happens to be looking at the right patch of sky on the right night, with the right conditions, the window is caught. If not, the window closes, the rock recedes, and the opportunity is gone until the next orbit brings it close again. In this case, the window was caught. May 10th, 2026, clear sky over southern Arizona, the Mount Lemon survey pointing in the right direction at the right moment, the software doing what it was built to do. A faint moving dot, flagged, reviewed, confirmed, reported. More observatories alerted, more measurements taken, orbit calculated, close approach confirmed. Now, to understand why this matters, and why 8 days of notice for a close approaching asteroid deserves more careful attention than the word routine would suggest, it helps to understand what an Apollo-class orbit actually means in practical terms. The solar system is not a flat disk of evenly spaced objects moving in tidy circles. It is a dynamic, gravitationally complex environment in which millions of objects occupy crossing, elliptical, inclined orbits that interact with each other and with the gravitational fields of the major planets over timescales, ranging from years to billions of years. The main asteroid belt, which sits between the orbits of Mars and Jupiter, is the source of most near-Earth asteroids. Objects in the belt are not static. Over millions of years, gravitational resonances with Jupiter and Mars slowly perturb their orbits, nudging them into regions where further perturbations can kick them onto paths that dip inside the orbit of Mars or Earth, or even Venus. Once an asteroid finds itself on an Earth-crossing orbit, it joins the Apollo class. The name comes from the first such asteroid to be catalogued with a well-determined Earth-crossing orbit, 1862 Apollo. discovered in 1932. There are now more than 15,000 known Apollo-class asteroids. They range in size from pebbles to objects several kilometers wide. The ones large enough to cause serious damage number in the thousands. The ones small enough to be common yet large enough to cause regional destruction, the Chelyabinsk to Tunguska size range, number in the hundreds of thousands, and most of them are unknown. 2026, JH2 is a perfectly ordinary member of this population. Its orbit takes it from roughly Earth's orbital distance at closest approach to the Sun out to approximately Jupiter's orbital distance at its farthest point, completing one circuit every 3.7 years. On most of those circuits, it passes nowhere near Earth. This particular orbit, the 2026 orbit, brought it to the closest approach it will make for the foreseeable future based on the data we now have. And because it was close, it was briefly bright enough to see. Think of it this way. The Catalina Sky Survey and the other near-Earth object search programs collectively photograph roughly a quarter of the entire sky on any given clear night. They return to already photographed regions on timescales of days to weeks, building a continuous and improving map of which objects are where. For large objects, the ones bright enough to be detectable from far away, this coverage is sufficient to build up a complete picture over years. For small objects like 2026, JH2, the coverage window is so narrow that the only reliable detection opportunity is during the close approach itself. This is not a criticism of the programs. It is simply an honest accounting of what is physically possible with current instruments operating under current constraints. The Catalina Sky Survey has been running since 1998. In that time, it has discovered tens of thousands of near-Earth objects and has played a central role in building the most comprehensive catalogue of solar system objects in human history. The work it does is extraordinary. It is also insufficient, not through any fault of its own, but because the problem it is trying to solve is harder than the universe is willing to make easy. 8 days of notice. For a rock the size of a blue whale, flying through the gap between our satellite infrastructure and the Moon, at 9 kilometers per second. By any measure, that is the system working. It is also, as we will come to see, a number that deserves more attention than it usually gets. Let's talk about the number 91,000 kilometers, because by itself it means almost nothing. Numbers at astronomical scale have a particular problem. They are too large to feel real and too small to feel cosmic, sitting in an uncomfortable middle distance where the brain registers them as significant without being able to attach any genuine intuition to them. 91,000 kilometers. You read that, and something in your mind files it under large and moves on. But that filing is wrong, and the wrongness is worth correcting, because once you understand what 91,000 kilometers actually means in the geometry of the Earth-Moon system, the flyby of 2026 JH2 stops being a news item and becomes something genuinely worth thinking about. Start with the Moon. The Moon orbits Earth at an average distance of roughly 384,000 kilometers. That number has been measured with extraordinary precision, because for decades we have been bouncing laser pulses off retroreflectors left on the lunar surface by Apollo astronauts and timing the return signal. We know the Earth-Moon distance to within a few centimeters, 384,000 kilometers. That is the baseline. 2026, JH2, at its closest point on the evening of May 18th, came in at approximately 91,000 kilometers. Divide one by the other, and you get roughly 0.24, not approximately a quarter of the way to the Moon. almost exactly a quarter of the way to the Moon. To put that in the kind of language that actually lands, if you drew a straight line from Earth to the Moon and divided it into 4 equal segments, 2026 JH2 passed through the first of those segments. It was well inside the Moon's orbit, not skirting the edge of it, now at the satellites. The ring of geostationary satellites sits at approximately 35,186 kilometers above Earth's equator. This is a specific altitude determined by orbital mechanics rather than engineering preference. At this distance, the orbital period of a satellite matches the rotational period of Earth, which means the satellite appears to hover stationary above a fixed point on the ground. This property makes geostationary orbit uniquely valuable for communications and weather observation, and as a result, it is one of the most populated orbital regions around Earth. The satellites in this band handle an enormous fraction of the world's telecommunications traffic, weather data, GPS correction signals, and television broadcasting. 2026, JH2 passed at 91,000 kilometers. The geostationary band sits at 36,000 kilometers. The asteroid flew outside the satellite ring, at more than twice the altitude of our highest operational infrastructure. In terms of impact risk to the satellites themselves, there was none. But the geometry tells a different story than simple safety. Think about what the asteroid actually threaded. Below it, at 36,000 kilometers, the arc of geostationary satellites. Above it, at 384,000 kilometers, the orbit of the Moon. 2026 JH2 flew through the space between those two boundaries, through the gap between the highest things we have placed in orbit and the natural body that has been orbiting us for 4.5 billion years. It did not graze either boundary. It flew well clear of the satellites and well inside the Moon's orbit simultaneously. This is what astronomers mean when they describe an approach like this as threading a needle. The needle in this case is the gap between human infrastructure and natural satellite, and a rock the size of a large marine creature flew through it at 9 kilometers per second without touching either side. It passed through the Moon's neighborhood about 3 hours before its closest approach to Earth, a detail that is easy to overlook but worth noting. The Moon itself was nowhere near the path of the asteroid at the time. The orbital geometry placed the Moon in a different part of its orbit during the flyby, but the rock still crossed the threshold of the Moon's orbital path, moved inside it, reached its closest point to Earth, and then began its retreat, all within the span of a few hours on a Monday night in May. Now let's talk about what this object actually was. Not in orbital terms, but physically. What kind of rock are we describing? The estimated size of 2026 JH2 is 16 to 35 meters in diameter. That range is wide, and as discussed in the previous section, the width is an honest acknowledgement of what we do and do not know about an object observed for only 8 days, with no radar observations completed before its departure. The size is derived from the absolute magnitude measurement and an assumed albedo, which is the fraction of incoming sunlight the surface reflects back. Different surface compositions reflect different amounts of light, and without spectroscopic measurements to determine composition, the albedo is an educated estimate based on the statistical distribution of surface types among known Apollo-class asteroids. So the size range is genuine uncertainty, not false precision made to look humble. 16 meters is approximately the length of a standard school bus, the kind that carries children to school in the morning. 35 meters is approximately the length of a blue whale, the largest animal that has ever existed on Earth, at any point in its 4 billion year history. The true size of 2026 JH2 is somewhere in that range. A school bus on one end, a blue whale on the other, probably somewhere in between. This is not large by asteroid standards. The rock that ended the Cretaceous period and caused the fifth mass extinction 66 million years ago was somewhere between 10 and 15 kilometers wide. That is 10 to 15,000 meters, compared to the 35-meter upper estimate for 2026 JH2. The difference in scale is so extreme that the comparison barely makes sense. But size is not the whole story, and the history of near-Earth objects contains some instructive examples of what rocks in this particular range are actually capable of. Those examples are coming in the next section, and they are worth approaching carefully rather than rushing toward. For now, stay with the physical picture of the object itself. 16 to 35 meters across. Unknown shape, because the observation window was too short for any detailed imaging, and no radar facility managed to get a confirmed return before the object departed. Unknown composition for the same reason. Almost certainly irregular rather than spherical, because small asteroids lack the self-gravity to pull themselves into a round shape, and tend instead to be potato-shaped or elongated, or simply lumpy in the way that rocks are lumpy when nothing has been smoothing them for billions of years. The surface of an object like this is likely covered in what planetary scientists call regolith, a layer of fine-grained material produced by billions of years of micrometeorite impacts gradually pulverizing the outer surface. It is cold, in the way that everything far from the sun is cold, though during its closer passages to the sun, it heats up enough that gases can sublimate from any volatile material trapped in its interior, though whether 2026 JH2 contained any such material is unknown. It orbits in darkness for most of its 3.7-year circuit, spending much of its time in the region between Earth and Jupiter, far from the warmth and light that made the inner solar system hospitable to life, and it was moving at 9.21 kilometers per second relative to Earth at the moment of closest approach. Let's be specific about what that speed means, because speed at astronomical scale has the same problem as distance. It registers as large, and then the brain moves on without actually reckoning with it. 9.21 kilometers per second is approximately 33,000 kilometers per hour. It is approximately 20,500 miles per hour. A commercial passenger aircraft cruises at roughly 900 kilometers per hour. 2026. JH2 was moving at roughly 37 times that speed. A high-powered rifle bullet, depending on the caliber, travels somewhere between 2 and 4 kilometers per second. 2026, JH2 was moving at more than twice the speed of a rifle bullet. The fastest aircraft ever built by human beings, the NASA X-43A scramjet testbed, reached approximately 11,200 kilometers per hour in 2004, an engineering achievement that required years of development and produced a vehicle that stayed aloft for about 10 seconds. 2026, JH2 covered 11,200 kilometers in roughly 20 minutes, without engines, without any propulsion whatsoever, simply by following the curve of space carved by the sun's gravity. By the standards of near-Earth objects, this speed is actually on the moderate end of the scale. Some Apollo-class asteroids approach Earth at velocities of 30 or 40 kilometers per second, 3 to 4 times faster than 2026 JH2. The speed of a given close approach depends on the geometry of the encounter, specifically the relative velocities of the asteroid and Earth in their respective orbits and the angle at which their paths cross. A slow, flat encounter, like 2026 JH2, indicates an orbit that is not dramatically inclined relative to Earth's orbital plane, one that crosses ours at a shallow angle. A fast, steep encounter indicates a more dramatically tilted orbit, punching through the ecliptic plane at a steep angle and spending less time in Earth's vicinity as a result. 9.21 kilometers per second, moderate for the class. Still, by any human engineering standard, an almost incomprehensible velocity for an object the size of a large marine mammal. Now let's follow the orbit itself, because the path 2026 JH2 travels is as revealing as the rock that travels it. Its orbital period is 3.7 years, which means it completes one full circuit around the Sun roughly every 3 years and 8 months. Earth completes its circuit in 1 year. Mars completes its circuit in roughly 1.88 years. Jupiter, the solar system's largest planet, completes its circuit in roughly 11.86 years. 2026, JH2 sits between Earth and Jupiter in terms of orbital period, spending portions of each circuit inside Earth's orbital path and portions of it out near the main asteroid belt, where most of the solar system's smaller rocky bodies reside. At its closest point to the Sun, what astronomers call perihelion, 2026, JH2 dips inside Earth's orbit. This is the defining characteristic of an Apollo-class asteroid. The perihelion distance is less than Earth's average orbital radius of 1 astronomical unit. At its farthest point from the Sun, what astronomers call aphelion, 2026, JH2 swings out to roughly the orbital distance of Jupiter, somewhere in the region of 5 astronomical units from the Sun. The transition from perihelion to aphelion and back again takes 3.7 years and covers an enormous range of the inner solar system. Think about what that journey looks like in physical terms. Starting from its closest approach to the Sun, 2026, JH2 swings out through the inner solar system, crossing Earth's orbital path, crossing the orbit of Mars, entering the asteroid belt proper, and threading through the scattered population of rocky bodies that occupy the region between roughly 2.2 and 3.2 astronomical units from the Sun. It reaches its farthest point in the outer belt, near Jupiter's orbital path, where the Sun is a much smaller and colder light source than anything we experience on Earth. Then it begins its return, falling back inward under the Sun's gravity, accelerating as it descends, crossing the belt again, crossing the orbit of Mars, crossing Earth's orbit, and completing its circuit. On the vast majority of these crossings, Earth is somewhere else. The geometry does not align. The two orbits intersect at specific points in space, but Earth and the asteroid have to be at those points simultaneously for a close approach to occur, and the timing of that simultaneity depends on the precise orbital periods of both bodies and the angles at which their orbits are oriented. The 2026 approach was one of those rare occasions when the geometry lined up closely enough to bring the two objects within a quarter of the lunar distance. Previous orbits may have produced similarly close approaches, or may have seen the two bodies pass each other at much greater distances. Without a longer observation arc, the historical close approach record for 2026, JH2 cannot be reconstructed with confidence. What shaped this orbit in the first place? The answer almost certainly begins in the main asteroid belt, where the gravitational influence of Jupiter acts as a kind of slow, patient sculptor, gradually altering the orbits of belt objects over millions of years through a mechanism called orbital resonance. When the orbital period of a belt asteroid falls into a simple numerical relationship with Jupiter's orbital period, say 2 to 1 or 3 to 1, Jupiter's gravity repeatedly pulls on the asteroid at the same point in its orbit, and those repeated tugs build up over time into significant orbital changes. The asteroid's orbit becomes more eccentric, more elliptical, until it begins to cross the orbits of the inner planets. Once an asteroid reaches a Mars-crossing orbit, Mars's gravity begins to play a role as well, and subsequent close approaches with Mars can kick the orbit into an Earth-crossing configuration. From there, the object joins the Apollo class, and its long-term orbital evolution is governed by a complex interplay of gravitational influences from all the inner planets, with Earth's gravity now occasionally significant enough to alter the orbit measurably during close flybys. This is the deep history of 2026 JH2, or something very like it. A body that originated in the main asteroid belt, perturbed over millions of years by Jupiter's gravity into an increasingly eccentric orbit, eventually finding itself on a path that crosses Earth's orbital lane on every circuit. Flying through the inner solar system on a trajectory that took millions of years to build and will persist for millions more, unless a sufficiently close planetary encounter alters it significantly. There is one more number worth establishing before we move on, and it comes from NASA's Center for Near-Earth Object Studies, which tracks close approaches and assigns what it calls a rarity value, based on how uncommon the combination of size and distance makes a given event. For 2026 JH2, the assigned rarity value was 2, indicating a notably unusual encounter even within the already unusual category of sub-lunar distance approaches. In all of 2026, 73 known asteroids passed within 1 lunar distance of Earth. 2026. JH2 was the 9th closest of all of them, 73. That number is worth sitting with. 73 asteroids passed within the Earth-Moon distance in the course of a single calendar year. Most were small, most were briefly detectable and then gone. Most generated no public attention, no news coverage, no emergency response. They came and went, logged in the Minor Planet Center's database, noted by the professionals who watch these things, and otherwise unremarked. The solar system is not the quiet, empty space of popular imagination. It is busy, in a specific and particular way, with rocks of various sizes passing through the inner system on their own schedules, regardless of whether any instrument happened to be watching. 2026. JH2 was the 9th closest of those 73 approaches, in a year that was itself not especially unusual by historical standards of near-Earth object traffic. What made it notable was the combination. Its size, putting it in the range of objects capable of real damage under the right circumstances. Its approach distance, close enough to be genuinely unusual even among close approaches. And its discovery timeline, compressing the entire arc from unknown to catalogued to departed into less than 2 weeks. A blue whale flying through the dark at 9 kilometers per second, threading the gap between our satellites and our moon, detectable for 8 days out of the billions of years it has been in existence. That is the object. Now we need to talk about what an object like this actually does when it does not miss. To understand what a rock the size of 2026 JH2 actually does, you need to understand something about the nature of kinetic energy, and specifically about how kinetic energy scales with mass and velocity in a way that consistently surprises human intuition. Kinetic energy, the energy of motion, is calculated using a formula that every physics student encounters early in their education. It is 1/2 times the mass of the object, multiplied by the square of its velocity. The squaring of the velocity is the important part. It means that when you double the speed of an object, you do not double its kinetic energy, you quadruple it. When you triple the speed, you multiply the energy by 9. The relationship between speed and destructive potential is not linear. It is exponential, and the numbers it produces at asteroid velocities are genuinely difficult to hold in the mind without some kind of scaffolding. Take an object somewhere in the middle of 2026, JHU's estimated size range, say 20 meters across. Give it a density consistent with a stony asteroid, which is the most common compositional type among Apollo-class objects, somewhere around 2 to 3 tons per cubic meter. Calculate the mass, then multiply by the square of the velocity, and divide by 2. What you get for a 20-meter stony asteroid entering Earth's atmosphere at typical impact velocities is a number measured in megatons of TNT equivalent. Not kilotons, not the scale of a large conventional bomb or even a tactical nuclear weapon. Megatons, the scale of strategic thermonuclear warheads. And this is for an object that, by asteroid standards, is tiny. The reason the energy numbers are so large is velocity. 2026 JH2 was moving at 9.21 kilometers per second at closest approach. Actual atmospheric entry velocities for near-Earth asteroids, depending on the geometry of impact, typically range from around 11 kilometers per second at the minimum, up to 70 or more kilometers per second for the fastest possible encounters. Even at the lower end of that range, the kinetic energy contained in a 20-meter stony object is staggering by any human reference point. And here is the crucial additional complication. This energy does not all arrive at the surface. Depending on the size, composition, and entry angle of the object, a significant fraction, sometimes almost all of it, can be deposited in the atmosphere before the object reaches the ground. This is where the physics of atmospheric entry becomes essential, and it is a phenomenon that surprises people when they first encounter it properly. The intuitive expectation is that a rock falling from space toward Earth will simply fall. It will descend through the atmosphere and either hit the ground or burn up entirely. The reality is more interesting and more violent than either of those simple outcomes, and it depends critically on the size of the object. Earth's atmosphere is not nothing. It is a column of gas roughly 100 kilometers deep, with most of its mass concentrated in the lowest 15 kilometers or so, and it exerts enormous aerodynamic forces on any object moving through it at high velocity. For very small objects, meteoroids a few centimeters or smaller, the atmosphere wins completely. The object heats up, ablates, and vaporizes before reaching the ground. What we see as a meteor, a shooting star, is the visible signature of this process, the glowing trail of superheated gas produced as the object sheds its outer layers at enormous speed. For very large objects, the ones measured in hundreds of meters or kilometers, the atmosphere loses. The object is simply too massive, carrying too much momentum, for the atmospheric drag to dissipate its energy before it reaches the ground. It punches through. It craters. The atmosphere absorbs some of its energy, but not enough to prevent a surface impact with catastrophic consequences. But for objects in the intermediate range, roughly 10 meters to perhaps 100 meters in diameter, neither outcome applies cleanly. The atmosphere is strong enough to significantly affect the object, but not strong enough to stop it entirely. And what happens in that middle zone is an airburst, a catastrophic structural failure of the object in midair, triggered by the aerodynamic forces exceeding the tensile strength of the rock itself. Here is how it works. As an asteroid enters the atmosphere at high velocity, it encounters air that it cannot move out of the way fast enough. The air in front of the object is compressed, heated, and forms a sheath of plasma around the leading face of the rock. The pressure on the front of the object is enormous. The pressure on the back is much lower, because the object is moving so fast that the air behind it cannot fill in quickly enough. This pressure differential, high in front and low behind, creates a force trying to tear the object apart from front to back. If the rock's internal strength is sufficient, it holds together long enough to reach the ground. If it is not, and for a loosely consolidated rocky object moving at tens of kilometers per second, the internal strength is almost never sufficient. The rock fragments. But the fragmentation does not simply break the object into a few large pieces. What happens at these velocities, under these pressures, is more like an explosion. The object disaggregates rapidly. The surface area exposed to the plasma sheath increases enormously as it breaks apart. The rate of energy deposition into the surrounding air spikes suddenly, and the result is an explosive release of energy equivalent to the object's full kinetic energy budget, occurring over a very short period of time at a specific altitude, an airburst. Not a nuclear explosion, which is powered by fission or fusion, but something that produces similar effects over a similar radius. An intense flash of light, a powerful pressure wave propagating outward in all directions, and a thermal pulse that can cause fires and burns within the immediate vicinity of the explosion point. The altitude at which the airburst occurs matters enormously for the pattern of damage on the ground below. An airburst at 30 kilometers altitude, like Chelyabinsk, spreads its shockwave over a very wide area, but at reduced intensity by the time it reaches the ground, because the wave has had 30 kilometers of travel time to expand and lose energy. An airburst at 5 kilometers altitude, like the best estimates for Tunguska, is much closer to the ground and delivers a much more concentrated shockwave to a smaller but much more intensely affected area beneath the explosion point. With that physics established, let us return to February 15th, 2013, and the morning over Chelyabinsk. It was a Thursday. The local time was just after 9 in the morning, and the city, of roughly 1 million people, was going about the ordinary business of a winter weekday. Children were in school, adults were commuting, or already at work. The sky was clear and bright in the way that Russian winter skies can be, cold and sharp, with the sun low in the south. Nobody was watching for anything unusual, because there was no reason to be watching. No telescope had detected what was coming. No system had issued any warning. The object had approached from the general direction of the sun, out of the portion of the sky where the sun's glare makes ground-based detection essentially impossible, and it arrived without any forewarning whatsoever. At 09:20 local time, a streak of light appeared in the southern sky. Witnesses described it as brighter than the sun, a claim that is not exaggeration but physics. At the peak of its atmospheric entry, the Chelyabinsk object was indeed producing more visible light than the sun as seen from the ground. Dashboard cameras, of which Russia has an unusually high density due to insurance fraud concerns, captured the event from dozens of angles. Security cameras, windows, smartphones, all of them recorded the same thing. A blindingly bright fireball crossing the sky from south to southwest, leaving a trail of superheated plasma and fragmenting debris behind it, growing brighter as it descended, and then, at roughly 30 kilometers altitude, producing a flash of light so intense that it temporarily bleached the video feeds of cameras pointing in its direction. Then came the shock wave. The object, estimated at approximately 17 to 20 meters across, had not reached the ground. It had exploded in the atmosphere, converting the bulk of its kinetic energy into a pressure wave that propagated outward from the explosion point at the speed of sound. The energy released in that airburst has been estimated at between 400 and 500 kilotons of TNT equivalent. For context, the atomic bomb detonated over Hiroshima in 1945 released energy equivalent to approximately 15 kilotons of TNT. The Chelyabinsk airburst was roughly 30 times more energetic than the Hiroshima bomb. It detonated over a populated area at an altitude of 30 kilometers, and the shockwave it produced reached the ground and spread outward, covering hundreds of kilometers before its intensity dropped below the threshold of structural damage. Across 6 cities in the Chelyabinsk Oblast, windows shattered. The shockwave was strong enough to blow in window frames, to knock people off their feet, to damage the structural integrity of buildings with weakened or poorly maintained facades. In the city of Chelyabinsk itself, approximately 3,000 buildings were damaged to some degree, and the injuries, all approximately 1,500 of them, came almost entirely from glass. This is the detail that lodges in the mind once you understand it. Not burns from the fireball, not blast injuries from the overpressure itself, which at ground level was not sufficient to cause direct bodily harm to most people. Glass. Because the fireball was so intensely bright that people throughout the region, seeing it cross the sky, walked to their windows to look. They pressed close to the glass or stood just beside it, drawn by the spectacle of the brightest thing any of them had ever seen in the sky. And they were standing at the glass, or just beside it, in the 10 to 30 seconds between the peak of the fireball and the arrival of the shockwave at their location. When the shockwave arrived, the windows exploded inward, and the people who had walked toward the light to see it better were standing directly in the path of the glass. There is something almost mythological about that sequence of events. The light that draws you to the window is the same event that is about to shatter the window. The impulse to look, which is among the most deeply human impulses there is, becomes in that specific context the source of injury. Nobody died in Chelyabinsk. Not one fatality is attributed to the impact event itself. But approximately 1,500 people were injured, the vast majority of them by the glass they had walked toward in order to see the sky better. The Chelyabinsk object was, by the best available estimates, somewhere between 17 and 20 meters across. 2026, JH2, at its lower size estimate, was 16 meters across. At its upper estimate, 35 meters. The Chelyabinsk object sits almost exactly within the size range we are discussing for 2026 JH2. This is not a coincidence selected for dramatic effect. It is the relevant comparison precisely because it tells us what the physics actually produces in the real world in a populated area for an object of this size class. An object at the upper end of 2026, JH2's size range, 30 to 35 meters, would produce a significantly larger airburst than Chelyabinsk. The energy scales roughly with the cube of the diameter for objects of similar density and entry velocity, which means a 35-meter object carries somewhere in the range of 10 to 15 times the kinetic energy of a 20-meter object. An airburst of that magnitude over a city would not produce 1,500 glass injuries. The overpressure itself would be sufficient to cause structural collapse, to overturn vehicles, to produce blast injuries of the kind associated with large conventional explosions. The radius of significant damage would extend for tens of kilometers. Still not a civilization ender, still not a city killer in the sense of total destruction, but something dramatically more consequential than Chelyabinsk, in the way that a Category 5 hurricane is dramatically more consequential than a Category 2, despite both being measurable on the same scale. This is the range we are talking about when we talk about 2026 JH2. Not extinction, not the end of a city, something in between, something that the historical record demonstrates can produce mass casualties and widespread structural damage across a significant metropolitan area, from an object that would have been undetectable until days before it arrived. But Chelyabinsk is not the upper ceiling of what this class of object can do. For that, you have to go back another 105 years to a remote region of Siberia that in June of 1908 had the misfortune of being directly below the trajectory of something somewhat larger. The Tunguska event remains the largest impact event in recorded human history. On the morning of June 30th, 1908, an object estimated at between 40 and 80 meters across entered the atmosphere over the sparsely populated basin of the Podkamenaya Tunguska River in what is now Krasnoyarsk Krai in central Russia. Like the Chelyabinsk object, it did not reach the ground. It exploded in the atmosphere at an estimated altitude of between 5 and 10 kilometers, in an airburst whose energy has been estimated at somewhere between 3 and 15 megatons of TNT equivalent, with most modern analyses clustering around 10 to 15 megatons. 10 to 15 megatons. The largest nuclear weapon ever detonated by any nation was the Soviet Tsar bomber, tested in 1961. It produced an explosion estimated at 50 megatons. The Tunguska airburst, from a rock that could have fit inside a large city block, produced somewhere between 1/5 and 1/3 of the energy of the largest nuclear weapon ever built, without a warhead, without any fissile material, simply by virtue of its mass and its velocity and the physics of atmospheric entry. The result was the flattening of approximately 2,000 square kilometers of Siberian forest. Roughly 80 million trees were knocked down, all of them pointing away from the epicenter of the explosion, creating a radial pattern of fallen timber that was still visible from the air decades later. It gave investigators their first clear evidence of where the explosion had occurred and at what altitude. The shockwave was detected by barometric stations across Europe and Asia. The atmospheric pressure pulse circled the Earth twice. Witnesses in the nearest villages, some 60 kilometers from the epicenter, were knocked off their feet. Windows were shattered, and several people and horses were reportedly thrown into the air by the force of the blast. Nobody died. The wilderness absorbed it. This is the number that matters most when thinking about Tunguska, because it carries an enormous implication. The event that flattened 2,000 square kilometers of forest and released the energy equivalent of 10 to 15 nuclear warheads happened over uninhabited wilderness, and its human toll was essentially zero. Had that same trajectory been aimed a few hundred kilometers to the west or south, it would have passed over populated regions of Russia or Europe. Had it occurred over London or Paris or Moscow, the death toll would have been measured not in hundreds or thousands, but in hundreds of thousands or millions, from an object that left no crater, that nobody saw coming, and that was entirely within the size range that our current catalogue covers for only a few % of known objects. Now step back from both events and ask a different question. How often does something like this happen? The answer is more frequent than most people expect, and the frequency is knowable because the solar system has been running this experiment on Earth for 4.5 billion years, and the geological and historical record contains the results. objects in the Chelyabinsk size range, roughly 10 to 20 meters, enter the atmosphere on average, perhaps several times per year globally, though most of them do so over ocean or uninhabited land, or at times and locations where no instruments happen to be watching. The Chelyabinsk event was unusual not primarily because of its size, but because of where it happened. Over a densely populated city with an unusually high density of dashboard cameras, producing an event that was recorded from dozens of independent angles and witnessed by hundreds of thousands of people simultaneously. Objects in the Tunguska size range, 40 to 80 meters, are less frequent. The best statistical estimates, derived from the size-frequency distribution of known near-Earth objects and calibrated against the impact record on the Moon, suggest that objects of this size strike Earth, on average, perhaps once every few hundred to 1,000 years. Once every few hundred to 1,000 years sounds reassuring until you remember that human civilization, in the sense of cities and written records and continuous institutional memory, is only about 5,000 years old. On that timescale, we might expect anywhere from 5 to 25 Tunguska-class events to have occurred. Most of them would have been over ocean. Some would have been over uninhabited land. The ones over populated areas would have been recorded as catastrophes. The 40 to 80 meter size estimate for the Tunguska object places it at the upper end of the range we are discussing for 2026 JH2, which had an upper size estimate of 35 meters. Tunguska and 2026 JH2 are therefore not identical in scale, but they are neighbors on the same size spectrum. Tunguska represents, with reasonable accuracy, the ceiling of what objects in and immediately above the 2026 JH2 size range can do. Chelyabinsk represents the floor. Between those two data points, both of them drawn from the last 115 years of observable history, the range of consequences for objects in this size class runs from 1,500 glass injuries and no fatalities all the way to potentially hundreds of thousands of casualties if the geometry had been different. What the geometry actually was, on both occasions, was fortunate. Chelyabinsk arrived at an angle that spread the shockwave across a broad area at reduced intensity. Tunguska arrived over wilderness. The outcomes were determined not by any warning system, not by any planetary defense capability, not by any decision made by any human institution. They were determined by where in the world the objects happened to arrive, which is to say, they were determined by chance. And here is the part of this that connects directly back to 2026 JH2 and to the 8-day warning window and to the system that caught it just in time. The Chelyabinsk object was detected by no instrument before it entered the atmosphere. Not because the survey programs were not running, they were. Not because nobody was watching, people were watching. The object came from the direction of the sun, out of the portion of sky blinded by solar glare, and it crossed the threshold of the atmosphere without a single prior observation. The warning time for Chelyabinsk was 0. 1,500 people were injured. Nobody died. Geography and geometry decided the outcome, and those variables are beyond any human control. 2026. JH2 gave us 8 days. 8 days in which its orbit was calculated, its close approach confirmed, its trajectory determined to be safe, and the public was informed. That 8-day window is what the system, at its current level of capability, produces for an object in this size range when everything goes right. 8 days is what working looks like. What Chelyabinsk demonstrated 13 years before 2026 JH2's flyby is what the alternative looks like, and the alternative is not a warning with hours to spare, or even minutes to spare. The alternative is no warning at all. The alternative is a morning in February, a clear winter sky, and a streak of light appearing in the south that nobody expected, nobody predicted, and nobody had any information about until the moment it was already there, already fragmenting, already converting its kinetic energy into the pressure wave that was about to reach the windows of a city. That is the range. 0 warning on one end, 8 days on the other. Both of them, in the long view of planetary history, are essentially the same moment. Both of them leave the question of consequences to geography and geometry, to the specific coordinates of the trajectory, and what happens to be occupying those coordinates when the rock arrives. 2026. JH2 did not arrive. It passed through. The trajectory was safe. The orbit was confirmed. The rock is gone. But the physics it embodies, the energy it carried, the damage it could have produced under different geometric circumstances, none of that is hypothetical. All of it is documented in the historical record by 2 events close enough to living memory that the photographs from one of them are available in any library, and the dashcam footage from the other has been watched hundreds of millions of times on the internet. The universe does not offer many direct demonstrations of the forces it is capable of. When it does, they are worth paying attention to. There is a map of the solar system that does not exist yet, not because nobody has tried to make it. The attempt has been underway for decades, funded by governments, prosecuted by observatories on multiple continents, supported by software systems of considerable sophistication, and staffed by scientists who have dedicated their professional lives to the project. The attempt is real and ongoing, and has produced extraordinary results. But the map itself, the complete accounting of every object in the inner solar system, capable of causing serious damage to something on the surface of Earth, that map remains unfinished. And depending on which size range you are asking about, it is unfinished to a degree that is either reassuring, concerning, or quietly staggering. The way planetary scientists think about this incompleteness is through a framework of 3 size tiers, each with its own detection history, its own level of catalogue completeness, and its own implications for what we do and do not know about our neighborhood. Understanding these tiers properly changes the way the story of 2026 JH2 reads, because it locates the rock within a larger picture of what humanity knows, what it is working to know, and what remains, for now and for the foreseeable future, genuinely unknown. Start at the top. Objects 1 kilometer across and larger are what planetary scientists sometimes call civilization enders. The terminology is not hyperbole. An asteroid 1 kilometer wide striking Earth would release energy on the order of tens of thousands of megatons of TNT equivalent. The immediate destruction in the impact zone would be total. The secondary effects, including the ejection of enormous quantities of dust and debris into the upper atmosphere, the resulting reduction in sunlight reaching the surface, the collapse of agricultural systems across large portions of the globe, would extend the consequences far beyond the immediate impact site and persist for years. A civilization ender is an object that, depending on where it strikes and a range of atmospheric and geological variables, could kill not millions but potentially billions of people and fundamentally alter the trajectory of human civilization. For this tier, the news is genuinely good. The Space Guard survey, mandated by the United States Congress in 1998 and prosecuted primarily through programs like the Catalina Sky Survey and the Lincoln Near-Earth Asteroid Research Program, has been specifically focused on cataloguing objects in this size range. As of current estimates, the catalogue of kilometre-scale and larger near-Earth objects is believed to be more than 90% complete. We have found the overwhelming majority of the objects large enough to end us. We know their orbits. We have projected those orbits forward in time. And none of the known ones are on a collision course with Earth in any time frame that human civilization is likely to be concerned about. This is a real achievement. It is worth stating clearly and without qualification, because it is easy, in a discussion of what we do not know, to lose sight of what we do know and what the people who built that knowledge accomplished. The near-complete catalogue of kilometre-scale near-Earth objects is one of the most consequential scientific achievements of the last 30 years, and it was done largely without public fanfare by a relatively small community of astronomers working at modest observatories on tight budgets. Now move down to the middle tier. Objects roughly 140 meters and larger are what planetary scientists call regional devastators, or, in more direct language, city killers. An object in this range striking a major metropolitan area would destroy it completely within the immediate impact zone and cause severe damage across a radius of tens to hundreds of kilometers, depending on the specific size and impact angle. An ocean impact from an object in this range would generate a tsunami capable of devastating coastal regions across an entire ocean basin. The human toll from a direct hit on a densely populated area would be measured in millions. In 2005, the United States Congress passed the George E. Brown Jr. Near-Earth Object Survey Act, which directed NASA to catalogue at least 90% of near-Earth objects 140 meters and larger by the year 2020. That goal has not been met. As of the most recent assessments available, the catalogue of objects in this size range stands at roughly 40% complete. We have found approximately 4 in 10 of the objects large enough to erase a major city. The remaining 6 in 10 are unknown. Their orbits have not been calculated. Their existence has not been confirmed. They are out there, in the inner solar system, crossing Earth's orbital path on their own schedules, and we do not know where they are. Pause on that number for a moment, not with alarm, because alarm is not the appropriate response to a statistical reality that has existed throughout the entirety of human history, and that has not yet produced a civilization-ending event. But with the kind of clear-eyed acknowledgement that the situation deserves. 6 in 10 objects large enough to destroy a major city are currently uncatalogued. This is not a crisis. It is a statement about the current state of a detection program that has been underfunded relative to its mandate for most of its existence, and that is making steady, if slower than promised progress, toward a goal that matters enormously. Now move down to the third tier, the tier that 2026 JH2 belongs to. Objects in the tens of meters range, the Chelyabinsk to Tunguska size class, the rocks capable of injuring thousands of people or flattening hundreds of square kilometers of terrain depending on where they arrive. For this tier, the catalogue is not 90% complete. It is not 40% complete. It is, by the best available estimates, a few percent complete at most. For every object in this size range that has been catalogued and given a provisional designation and had its orbit calculated, there are likely dozens or hundreds of similar objects following similar orbits that remain entirely unknown. The reason for this dramatic incompleteness is physics, the same physics that made 2026 JH2 invisible until 8 days before its closest approach. Smaller objects are fainter. they reflect less sunlight. They cross the detection threshold of ground-based survey telescopes only when they are already close to Earth. And close means days of warning rather than weeks or months or years. The survey programs that have done so well at cataloguing large objects are operating near the limits of what ground-based optical telescopes can achieve at this size range, and pushing significantly further requires either dramatically larger ground-based instruments or, more promisingly, a space-based infrared telescope operating beyond the interference of the sun's glare. Within that system, there are people whose specific job is to watch the close approach tables, to track the newly discovered objects, to run the automated impact assessment software that evaluates every new discovery against the known orbits of all other solar system bodies and flags anything that might represent a concern. NASA runs two such systems. The first is Sentry-2, an impact monitoring system maintained at the Jet Propulsion Laboratory in Pasadena, California, which maintains a continuous risk table of all known near-Earth objects with non-zero calculated impact probabilities extending a century into the future. Sentry-2 runs automatically, continuously updating its assessments as new observations refine orbital solutions and as the positions of Earth and other planets change over time. The second system is Scout, which operates on a faster timescale and serves a different purpose. Where Sentry-2 tracks known objects across long time frames, Scout evaluates newly discovered objects in real time. It processes the initial observations submitted to the Minor Planet Center and estimating the probability of Earth impact based on the limited early data available for a freshly found asteroid. Scout is the system that runs the first assessment of a new object within hours of discovery, before the orbital solution has been fully constrained, and it is Scout's output that determines whether a new discovery warrants urgent follow-up observations from additional facilities. When 2026 JH2 was reported to the Minor Planet Center on May 10th, Scout ran its automated assessment within hours of the initial report. The result was a non-zero impact probability. This is standard for any newly discovered object whose orbital solution is based on only a few hours of observations and whose trajectory therefore carries real uncertainty. A non-zero Scout probability does not mean a confirmed threat. It means the current data is insufficient to rule out impact, which is true of almost every newly discovered object in its first hours of existence as a catalogue entry. As additional observations accumulated over the following hours and days, observations from the Farpoint Observatory in Kansas, from other facilities across the United States that picked up the object after the Minor Planet Center, circulated the discovery report. Scout's probability estimate was continuously revised. The orbital solution tightened, the uncertainty shrank, the range of possible trajectories consistent with all available observations narrowed, and as it narrowed, the trajectories that passed through Earth shrank to zero. Within roughly 48 hours of the initial discovery, the object was confirmed safe. The Scout probability reached zero. The Sentry-2 risk table never required an entry for 2026 JH2 because by the time the orbital solution was sufficiently mature to enter the long-term monitoring system, the impact probability was already zero. This process, from discovery to safe confirmation in roughly 2 days, is the routine operation of a detection system that handles dozens of new near-Earth object discoveries every month. The speed and reliability of this pipeline is genuinely impressive. The limitation is not in the processing, but in the input. The pipeline can only work with objects that have already been discovered, and the discovery depends on the physics of detection that we have already examined in detail. there are astronomers who watch this process not just professionally, but publicly. Gianluca Masi, an Italian astronomer who runs the Virtual Telescope project from Ceccano in central Italy, hosted a live observation of 2026 JH2 on the evening of May 18th, beginning at 19:45 Universal Time, capturing the asteroid as it brightened toward its peak magnitude of approximately plus 11.5 near closest approach, and streaming the images to anyone in the world with an internet connection. Magnitude plus 11.5 means the object was detectable with a modest amateur telescope or strong binoculars at closest approach, though it was moving fast enough across the sky that tracking it required knowing precisely where to look. For the general public, the event was invisible to the naked eye. For anyone with the right equipment and the coordinates provided by the Minor Planet Center's close approach tables, it was briefly, tangibly real. A faint point of light moving against the stars, faster than any star moves, on its way through and then gone. That visibility, brief and modest as it was, is worth noting because it represents one end of a spectrum of what detection actually means in practice. At one end, there is the Survey telescope on a mountain in Arizona, running its automated scans, flagging its candidates, submitting its reports to Cambridge, feeding the global pipeline that converts a moving dot into a catalogued object with a name and an orbital solution. At the other end, there is a person in Italy pointing a telescope at a set of coordinates and watching a faint dot move across the field of view, streaming it live to anyone in the world who wanted to watch. Both of these things happen simultaneously on the same evening, for the same object, and together they represent the full range of what watching the solar system looks like in practice. The industrial-scale automated survey at one end, the individual human eye at the other. Between them, a pipeline of software and communication and collaborative observation that transforms a faint moving pixel into a known piece of the solar system's population, however briefly. 8 days of notice. Across all of the ground-based survey programs currently operating, all of the software, all of the observatories, all of the Minor Planet Center's processing infrastructure, all of the Scout and Sentry 2 automated assessment systems, the combined output of the global near-Earth object detection network for an object in the size range of 2026 JH2, working at its current level of capability under good observing conditions, with the object approaching from a detectable direction rather than out of the sun's glare, is 8 days. That is not a failure. That is not a scandal. That is an honest accounting of what is physically achievable with the instruments we have currently deployed, pointed at a universe that contains far more objects in this size range than our catalogues currently reflect. What it means in practice is something we will need to return to shortly. But first, it is worth understanding not just what we cannot see, but what was happening in the same patch of sky during the same week, because 2026 JH2 was not the only rock in the neighborhood that week, not by a considerable margin. On the evening of September 26, 2022, a spacecraft the size of a vending machine traveling at approximately 6 kilometers per second collided deliberately with an asteroid. The asteroid was called Dimorphos. It was a small rocky body, roughly 160 meters across, orbiting a larger asteroid called Didymos in a binary system that had been selected specifically for this purpose. The spacecraft was NASA's Double Asteroid Redirection Test, DART, and the collision was not an accident. It was the culmination of years of planning, engineering, and orbital calculation, designed to answer a question that planetary scientists had been asking theoretically for decades. if you hit an asteroid hard enough, can you actually change where it is going? The answer, it turned out, was yes. Before the impact, Dimorphos completed one orbit around Didymos every 11 hours and 55 minutes. After the impact, that period had shortened by 33 minutes to approximately 11 hours and 23 minutes. The DART spacecraft, massing roughly 570 kilograms, had transferred enough momentum to a 160-meter asteroid to measurably alter its orbital period. The change was small in absolute terms, 33 minutes out of nearly 12 hours. But in the context of planetary defense, small is sufficient, because the strategy does not require stopping an asteroid. It requires nudging one, changing its speed by a tiny amount so that, over the subsequent orbits, the accumulated difference in position grows large enough that the asteroid no longer intersects Earth's orbital path at the same moment Earth happens to be there. Time is the multiplier. The nudge is small. The lead time is everything. This is the principle that DART proved. Not hypothetically, not in a computer model, but physically, against a real asteroid, with the results confirmed by multiple independent observations from Earth-based telescopes and from the European Space Agency's Hera mission, which subsequently visited the Didymos system to document the aftermath in detail. The ejector plume produced by the impact, the material blasted off Dimorphos's surface by the collision, contributed significantly to the momentum transfer, amplifying the deflection beyond what the spacecraft's own momentum alone would have produced. This ejector enhancement is now a documented and quantifiable component of kinetic impact emissions, and it improves the efficiency of deflection relative to pre-DART models. The principle is real. A kinetic impactor can change an asteroid's orbital trajectory by a measurable and meaningful amount. The physics is confirmed, the engineering is demonstrated, and the lesson of DART, properly understood, is simultaneously encouraging and clarifying. Encouraging because it means the tool exists, clarifying because of what DART was not, and this distinction matters enormously when you try to apply the lesson of DART to the situation of 2026 JH2. DART was one test, conducted against one carefully selected target. It was under conditions chosen specifically to make the result easy to measure and verify. Dimorphos was selected because its orbit around Didymos gave scientists a way to detect very small changes in orbital period that would have been essentially undetectable for an asteroid orbiting the Sun alone. The mission was planned over years. The launch window was calculated well in advance. The spacecraft took 10 months to reach its target after launch. The entire timeline, from mission conception to impact, spanned the better part of a decade. A real threat scenario would not offer any of those conveniences. A real threat would be an object discovered days or weeks, or at best months, before its projected impact date. Its orbit would carry it not around a companion asteroid, but directly toward Earth, and against which the response timeline would be compressed into whatever window the detection system happened to provide. For an object in the size range of 2026 JH2, that window, as we have established, is measured in days. The DART mission proved that the physics of deflection works. It did not build a standing deflection capability. There is no fleet of DART-like spacecraft sitting fueled on launch pads, ready to be directed at a newly discovered threat on short notice. The engineering challenge of building such a system, the cost, the lead time required to construct and test multiple vehicles, the political will required to fund and maintain a capability whose need might not materialize for decades, none of that has been resolved. DART showed that water puts out fire. The fire department has not yet been built, and the physics makes the gap worse the more carefully you examine it. A kinetic impactor does not stop an asteroid. It changes the asteroid's velocity by a tiny fraction, and that tiny change compounds over subsequent orbits until it grows into the difference between a hit and a miss. The shorter the time between impact and the projected Earth encounter, the smaller that compound growth, and therefore the larger the spacecraft, and the higher the impact velocity you need to achieve the same deflection. A mission launched 10 years before a projected impact needs to deliver a fraction of the momentum that a mission launched 1 year before would need to deliver. A mission launched 1 month before a projected impact needs to deliver so much momentum that the engineering requirements begin to approach the physically impossible for objects in the larger size ranges. For 2026 JH2, with 8 days of warning, the deflection question is essentially academic. Not because the physics fails completely at 8 days, but because 8 days is not sufficient time to design, build, fuel, and launch a spacecraft, regardless of what the physics allows. The detection window and the response capability do not exist on the same timescale, and that mismatch is the central unsolved problem in planetary defense for objects in this size range. Now let's talk about the week itself. Because 2026, JH2 was not the only rock moving through the Earth-Moon neighborhood during those days in May, and the company it was keeping adds a dimension to the story that deserves its own space. Near-Earth object close approach tables are publicly available. NASA's Jet Propulsion Laboratory maintains them, updated continuously as new observations refine orbital solutions and new discoveries are added. During the week surrounding 2026, JH2's closest approach, anyone consulting those tables would have found an unusually crowded list. Not one object passing inside the Earth-Moon distance. Around 8 of them, spread across a period of days, most of them recently discovered, most carrying designations from the same series as 2026 JH2. One of the most notable companions was 2026 JK2, an object estimated at around 26 meters across, moving at approximately 20.5 kilometers per second, which made its closest approach at about 1.24 lunar distances, just outside the boundary of the Earth-Moon distance, a day before 2026 JH2's passage. At its higher velocity and steeper orbital inclination, 2026 JK2 was moving significantly faster than 2026 JH2 and approached at a greater distance, consistent with a pattern that emerges when you examine the full cluster. The objects that came closest to Earth tended to be the slower moving ones on flatter orbits, while the faster, more steeply inclined objects tended to pass at greater distances. This pattern has a physical explanation. An asteroid on a nearly flat orbit, one that crosses Earth's path at a shallow angle, travels almost alongside Earth for a period as it crosses, and can therefore ease in close before the geometry separates them again. An asteroid on a steeply inclined orbit punches through the ecliptic plane at a steep angle and is gone quickly, passing through the neighborhood at high relative speed and departing before the geometry can bring it into a very close approach. When you plot the orbits of the entire cluster and follow them backward from their Earth crossing points into the outer solar system, they diverge. At their furthest from Earth, at their aphelia, out near the asteroid belt, these objects are on entirely different orbits. Different shapes, different inclinations, different orientations relative to the plane of the solar system. By every measure of orbital dynamics, they are unrelated objects that have been following independent paths for millions of years, perturbed by different planetary encounters, shaped by different resonance histories, but follow them inward toward Earth, and they converge. The paths draw together, crowding into the same region of space near Earth's orbital path, arriving in the same narrow window of time. This convergence requires an honest interpretation. Part of it is an observational artifact. The only asteroids in this size range that appear in any close approach table are the ones that came close enough to be detected, which means close enough to Earth to enter the detection range of the survey telescopes. If you only ever see the rocks that pass close, then naturally every rock you have catalogued passes close. The convergence looks tighter than it really is, because you are looking at a biased sample. The rocks that pass through the same neighborhood at greater distances during the same week are simply unknown, uncatalogued, undetected, but not all of the convergence is artifact. There is genuine physics in the inner solar system that causes the density of Earth-crossing orbits to be higher in certain regions and at certain times than in others, driven by the gravitational focusing effect of Earth and the other inner planets, which tends to concentrate the orbits of nearby objects in ways that are real rather than illusory. The honest read, after subtracting the observational bias, is that the week was genuinely busier than average, not dramatically so, but measurably. 8 rocks visible, an unknown number invisible, all of them following their own paths through the neighborhood, all of them doing exactly what they have been doing for millions of years, regardless of whether the survey telescopes happen to be pointing in the right direction on any given clear night. And out at the other end of the size spectrum, far above the detection horizon, even for the busiest weeks of near-Earth object traffic, there is one object whose story is almost the precise inverse of 2026 JH2's. An object that is large enough to find decades in advance, whose orbit has been refined over more than 20 years of continuous observation, and whose 2029 close approach has been anticipated by planetary scientists since its discovery. Its designation is 9999942, Apophis. Its popular name, assigned after its discovery prompted a brief period of genuine scientific concern about its trajectory, is the god of chaos. Apophis is approximately 340 meters across. At that size, it is firmly in the regional devastation class, large enough to cause catastrophic destruction across a wide area on land or to generate a significant tsunami if it struck the ocean. When it was discovered in 2004, initial calculations of its orbit produced an impact probability for April 13, 2029 that briefly reached as high as 2.7%, which made it, for a short period, the most dangerous known asteroid in the solar system by the standard risk metrics used by planetary defense scientists. Subsequent observations accumulating over months and then years rapidly refined the orbital solution and brought the impact probability down to 0. Apophis is not going to hit Earth on April 13, 2029. Its trajectory has been calculated with sufficient precision to rule that out with high confidence. What it is going to do is pass within approximately 32,000 kilometers of Earth's surface, closer than the geostationary satellite ring, the closest approach by an asteroid of its size in recorded observational history. The 2029 flyby of Apophis will be an extraordinary scientific opportunity. At its closest approach, the asteroid will be visible to the naked eye from parts of the world, appearing as a moving star crossing the night sky at a speed perceptible in real time. Multiple space agencies have planned or proposed missions to rendezvous with Apophis during or around its 2029 passage, taking advantage of the close approach to study the asteroid's surface, composition, rotation state, and internal structure at a level of detail that would be impossible from Earth's distance under normal circumstances. The gravitational influence of Earth during the 2029 flyby will measurably alter Apophis's orbit. The precise details of that alteration depend on the exact geometry of the encounter, and the altered orbit will determine the timing and geometry of all subsequent close approaches. Scientists are monitoring this carefully because the post-2029 orbit of Apophis will need to be reassessed for any potential impact scenarios in subsequent decades. The current assessment is that no impact risk exists through at least 2100, but the 2029 flyby will refine that assessment significantly. The contrast with 2026 JH2 is exact and instructive. Apophis has been known since 2004. Its orbit has been observed and refined across more than 2 decades of continuous tracking. Scientists have had 25 years to study its trajectory, model its gravitational interactions with Earth and the Moon during the 2029 flyby, and plan observations for the encounter itself. If the orbital calculations had at any point returned a non-zero impact probability for 2029, there would have been years of runway available to design and execute a deflection mission of exactly the kind that DART proved is physically possible. The difference between Apophis and 2026 JH2 is size. Apophis is 340 meters across. 2026 JH2 is 16 to 35 meters across. Apophis is large enough that it became detectable more than 20 years before its closest approach, giving the planetary defense community all the time it needed to understand the threat and respond if necessary. 2026 JH2 is small enough that it became detectable 8 days before its closest approach, giving the planetary defense community time to confirm it was safe and nothing else. Same solar system, same detection network, same response capability. 2 completely different outcomes in terms of warning time, simply because one object is large enough to see from far away, and the other is not. This is the frontier. Not the dramatic frontier of Hollywood imagination, where a plucky team of astronauts launches at the last minute and saves the world. The actual frontier, a detection network steadily improving its coverage of the large end of the size spectrum, while the small end remains nearly empty. A deflection technology proven in principle, but not yet operationalized. And a mismatch between the warning times the system produces and the response times that any realistic intervention would require. The rocks keep coming. The survey telescopes keep running. The close approach tables keep updating. And somewhere in the dark, moving on orbits that Jupiter shaped over millions of years and that no instrument has yet caught, there are objects in the 2026 JH2 size range following paths that will bring them close to Earth on dates that nobody has yet calculated, because nobody yet knows they exist. That is the frontier, not a crisis, not a reason for alarm, but a clear and honest picture of where the capability currently stands and how much remains to be built. At 21:23, Universal Time on May 18, 2026, JH2 reached its closest point to Earth. There was no announcement. No instrument registered the moment as significant in any way that would have been perceptible to a human observer. The asteroid did not pause. It did not slow. It continued on its path at the same velocity it had been traveling before the closest approach, and would continue to travel after it, 9 kilometers per second, indifferent to the milestone the moment represented for the people who had been tracking it. The closest approach was not an event in the way that a collision is an event, or an explosion, or a landing. It was a point on a curve. The curve continued. Within minutes of that closest point, the geometry of the encounter began to reverse. The distance between the asteroid and Earth, which had been shrinking for days as the rock descended through the inner solar system toward its perihelion, began to increase again, slowly at first, then more rapidly, as the orbital paths diverged. The rock that had been approaching for weeks was now receding, and it would continue to recede for the next 3.5 years, until the geometry of the solar system brought it back to the inner system on its next orbit. By the time most people in the United States sat down to dinner on the evening of May 18, 2026, JH2 was already tens of thousands of kilometers farther away than it had been at its closest point. By midnight, it was 100,000 kilometers gone. By the following morning, it had crossed back outside the Moon's orbital distance, moving outward, away from the Sun, beginning the long arc of its retreat toward the asteroid belt. Let's follow it. The orbital path of 2026, JH2, now that we have enough observations to reconstruct it with reasonable confidence, is an ellipse with the Sun at one focus. All orbits in the solar system are ellipses, a consequence of the inverse square law of gravitational attraction that Johannes Kepler described in the early 17th century and Isaac Newton later derived from first principles. The specific shape of 2026 JH2's ellipse is determined by two numbers: its semi-major axis, which describes the average size of the orbit, and its eccentricity, which describes how elongated the ellipse is relative to a perfect circle. 2026. JH2's orbit is significantly elongated. At its closest point to the Sun, its perihelion, it dips inside Earth's orbital path. At its farthest point from the Sun, its aphelion, it swings out to approximately the orbital distance of Jupiter. The ratio between these two distances gives the orbit its characteristic shape: a long, stretched ellipse that carries the rock from the warm inner solar system, where Earth and Venus and Mars orbit, all the way out to the cold, dark outer reaches of the inner solar system, where Jupiter's gravity begins to exert its slow and patient influence. The journey from perihelion to aphelion, from closest to farthest from the Sun, takes roughly half of the 3.7-year orbital period, approximately 22 months. During those 22 months, 2026 JH2 travels outward through the inner solar system, crossing the orbit of Mars, entering the asteroid belt, threading through the scattered population of rocky bodies that occupy the region between Mars and Jupiter, and finally reaching its farthest point from the Sun in the outer belt, before beginning its return. Picture that journey in physical terms, and take your time with it, because this is a journey worth following slowly. Leaving the vicinity of Earth in the days after May 18th, the rock moves outward, climbing against the Sun's gravitational pull, the way water climbs against gravity when you push it uphill, decelerating gradually as it rises. The Sun, which from Earth's distance presents itself as a disk roughly half a degree across, a disk warm enough to tan skin and bright enough to damage unprotected eyes, begins to shrink as the distance grows. From the perspective of the asteroid, if such a perspective were possible to inhabit, the Sun would diminish week by week, losing its dominance over the sky by degrees, becoming something more like a very bright star and less like a presence. The rock crosses the orbit of Mars. Mars itself is somewhere else in its own orbit, following its own ellipse around the Sun at its own pace, and the two objects do not encounter each other. The crossing is purely geometric. 2026. JH2 passes through the region of space that Mars periodically occupies, at a moment when Mars is not there. The inner solar system is vast enough that orbital crossings of this kind happen constantly without any actual meeting between the objects whose orbits intersect. Beyond the orbit of Mars, the character of the space changes. The rock enters the inner edge of the asteroid belt, the broad ring of debris left over from the formation of the solar system that Jupiter's gravity prevented from ever coalescing into a planet. The belt is nothing like its popular depiction. In films and games, it is imagined as a dense, chaotic swarm of tumbling boulders, impossible to navigate without constant collision. The reality is almost the opposite. The asteroid belt is so vast, spanning hundreds of millions of kilometers in radial extent, and the objects within it are so sparsely distributed that the average distance between belt objects is measured in hundreds of thousands of kilometers. A spacecraft passing through the asteroid belt has an extremely small probability of coming within visual range of any object larger than a pebble, but the belt is not empty. Hundreds of thousands of objects large enough to be catalogued move through it on their own orbits, and many millions more that are too small to detect at current capabilities. The rock that was briefly known as 2026, JH2, threads through this population, one irregular, unnamed object among many, indistinguishable from the surrounding debris to any external observer, carrying no catalogue entry in this context, no designation, no record of the 8 days in May when it was briefly something other than anonymous. In the outer belt, approaching aphelion, the rock slows. This is Kepler's second law made physical. The conservation of angular momentum means that as the rock moves farther from the Sun and the gravitational pull weakens, it must slow down to maintain the geometry of its elliptical path. At aphelion, near Jupiter's orbital distance, 2026 JH2 is moving at its minimum speed, perhaps 2 or 3 kilometers per second relative to the Sun, a pace that is still extraordinary by any human standard, but is leisurely compared to the 9 kilometers per second it was doing during its close passage by Earth. At this distance from the Sun, the temperature of the rock's surface would be somewhere around -150 degrees Celsius, or colder, depending on how much sunlight its surface reflects and how efficiently it radiates heat back into space. There is no atmosphere to retain warmth, no geological activity to generate heat from within, no proximity to the Sun sufficient to warm the surface significantly. The rock exists in a state of profound cold, the deep cold of the outer solar system, a cold that human engineering goes to considerable lengths to protect spacecraft from when they venture into these regions. Jupiter is enormous from this distance, not as large as the Sun appears from Earth, but large enough to be a visible disk rather than a point of light, its cloud bands faintly visible to a sufficient optical instrument, its 4 largest moons, the Galilean moons that Galileo first observed in 1610, tracing their own orbits around it on periods ranging from less than 2 days to just under 17 days. Jupiter's gravitational field extends far beyond its visible disk, and at the distance of 2026, JH2's aphelion, that field is the dominant gravitational influence after the Sun itself. It is Jupiter that shaped this orbit, not in a single dramatic event, but over millions of years of slow, repeated perturbation. Each time 2026, JH2's orbit brought it into a gravitational resonance with Jupiter, Jupiter's gravity nudged the orbit slightly, incrementally altering its shape and orientation over timescales so long that the change per orbit was utterly imperceptible, but accumulated across hundreds of thousands of orbits into a dramatic transformation of the object's trajectory. The rock that was once a member of the main asteroid belt, following a nearly circular orbit in the quiet middle regions of the belt, was gradually pushed onto an increasingly eccentric path, its orbit stretching and tilting, until it eventually crossed the orbit of Mars and then of Earth and became the Apollo-class object that, millions of years later, would briefly appear on a monitor in Arizona on May 10, 2026. Then the return. The rock reaches aphelion and begins to fall back inward, gravity reclaiming it, the sun's pull growing stronger as the distance shrinks, the rock accelerating steadily as it descends back through the outer belt, back through the inner belt, back across the orbit of Mars. The sun grows larger and warmer ahead. The journey back to perihelion takes another 22 months, and by the time the rock reaches the inner solar system again, Earth will have completed nearly 2 full orbits of its own. Whether the geometry of that return brings 2026, JH2 close to Earth again, is a question that the current orbital solution cannot answer with high confidence. The 8-day observation arc limits the precision of forward projection. The orbital solution we have is reliable for the immediate future, reliable enough to confirm that no impact is possible in the near term, but becomes progressively less certain as it is projected across multiple orbital periods. Small uncertainties in the current solution, uncertainties that are inherent in any short observation arc, grow larger with each projected orbit. Until after several circuits, the solution becomes too uncertain to make confident predictions about close approach distances. Before May 10, 2026, this rock had no name. Sit with that sentence for a moment, not as a scientific statement, but as a fact about the relationship between human knowledge and the universe it inhabits. The rock did not need a name. It was not waiting for one. It had been following its ellipse around the sun, long before the concept of naming existed on the third planet from that sun, long before there were minds on that planet capable of observing it, long before there were instruments capable of detecting it, even if such minds had existed and had thought to look. The name 2026 JH2 is a human artifact, as contingent and temporary as any other product of a human activity. It exists in a database in Cambridge, Massachusetts. It exists in the memory of the software systems that track the object during its brief period of visibility. It exists in this account, and in the accounts of the observatories that contributed measurements to its orbital solution. In no other sense does it exist. The rock itself is indifferent to all of this. It is following the same orbit it was following before May 10th, and will follow after the name has faded from human records. It is the same temperature it was before the name was assigned. The same shape, the same composition, the same mass. The name changed nothing about the rock. It changed only its relationship to human knowledge, briefly elevating it from the vast population of unknown objects into the much smaller population of known ones, before the geometry of the solar system carried it back below the detection horizon and returned it, functionally, to the unknown. How many times has something like this happened for this particular rock over the billions of years of its orbit? How many previous close approaches brought it within detectable range of the inner solar system, at a time when no instrument was running, or no instrument existed, or the sky was clouded over the one observatory that might have caught it? The question is unanswerable in practice, but in the statistical sense, the answer is almost certainly many. An object following an Apollo-class orbit for millions of years will have made close passes to Earth on numerous occasions. Each one was a window of potential visibility. Each window opened and closed without detection, because the instruments did not exist or were not pointing in the right direction, or the conditions were not right, or the approach was not quite close enough to cross the detection threshold, even if all of those other things had been favorable. The 2026 approach was the one that was caught. One window, out of many. The same rock, briefly knowable, briefly known, and now receding back into the long anonymity that is its natural condition. 3 days before 2026, JH2's closest approach, on May 15, 2026, another asteroid passed Earth. Its designation is 2026 JH1. It was roughly the size of a commercial passenger aircraft, and it passed at approximately 5.9 million kilometers from Earth, which is nearly 16 times the Earth-Moon distance. It attracted almost no public attention. It was logged in the close approach tables, its orbit calculated, its flyby confirmed as safe, and the survey telescopes moved on to the next candidate in the queue. 2026 JH1 is the baseline, an aircraft-sized rock passing at 16 lunar distances, noted by the professionals who watch these things and otherwise unremarked. The solar system produces these events continuously. The close approach tables list them in the dozens every month. Objects of various sizes passing at various distances, each one catalogued, each one assessed. Each one determined to be safe and then allowed to continue on its way without further comment. Most of what passes through the inner solar system goes unnoticed by anyone outside the small community of planetary scientists and amateur astronomers who follow the close approach tables as a matter of professional interest or personal curiosity. The universe does not announce itself. It does not pause for human attention or arrange its schedule around human observing runs, or clear the clouds from Arizona mountaintops on the nights when a discovery would be most convenient. The rocks follow their orbits. The planets follow their orbits. The survey telescopes photograph their patches of sky on the clear nights they are given, and the close approach tables update quietly and continuously. It is a running account of a neighborhood that is considerably more active than its reputation suggests. 2026. JH2 is gone now. It reached its closest point at 21.23 Universal Time on May 18th, and it has been receding ever since. By the time this account ends, it will be millions of kilometers farther away than it was at closest approach, moving outward, cooling, dimming, following the long arc of its ellipse back toward the asteroid belt and the cold dark of aphelion. In a few weeks, it will be beyond the reach of any ground-based telescope currently operating. In a few months, it will be crossing the orbit of Mars. In a few years, it will be near Jupiter, cold and slow, one anonymous rock among the millions that occupy the middle distance of the solar system. And the survey telescopes will keep running. The close approach tables will keep updating. The Minor Planet Center will keep receiving reports, assigning designations, filing orbital solutions. The universe will keep producing close approaches, some detected, most not, in a continuous and unhurried procession that has been going on since long before the first telescope was pointed at the sky, and will continue long after the last one is retired. The rock is back in the dark, where it has always been, where it will remain. The story of 2026. JH2 ends with the rock gone and the gap intact. 8 days of warning. A detection system that performed exactly as designed. A deflection capability proven in principle and absent in practice. And a catalogue of tens of meters class objects that covers a few % of what is actually out there. That is where things stand today. But the question of where things will stand in 10 years or 20 is a different question, and the answer is more encouraging than the current picture might suggest. Not because the problem is about to be solved, but because the tools required to make meaningful progress are either already built or already in development, and the people building them understand with unusual clarity what the problem actually is and what solving it would require. Start with the detection side, because detection is the prerequisite for everything else. You cannot deflect an object you have not found, and you cannot find an object you cannot see. The fundamental limitation of the current ground-based survey network, as we have examined in detail, is the faintness of small asteroids at the distances where they would need to be detected to provide warning times longer than days. Ground-based optical telescopes are working near the physical limits of what reflected sunlight detection can achieve for objects in the tens of meters range, and pushing significantly further with ground-based instruments alone would require telescope apertures and survey speeds that are not economically or practically achievable in the near term. The solution that planetary scientists have been advocating for years, and that NASA has been developing with increasing seriousness, is a dedicated space-based infrared survey telescope operating in an orbit that allows it to observe the inner solar system without the interference of the sun's glare that limits ground-based systems. The specific mission that has been in development is called NEO-Surveyor. It is designed to operate at the Sun-Earth L1 Lagrange point, a gravitationally stable location approximately 1.5 million kilometers from Earth in the direction of the Sun, where a spacecraft can maintain a relatively fixed position relative to Earth while looking outward into the inner solar system. From this vantage point, NEO-Surveyor would observe in infrared wavelengths rather than visible light, which offers a significant advantage for asteroid detection. The advantage comes from the physics of thermal emission. Every object in the solar system absorbs sunlight and re-emits it as infrared radiation, and the amount of infrared radiation an object emits depends on its temperature and its size, rather than primarily on its surface reflectivity. A dark asteroid that reflects very little visible light, and would therefore appear faint in a visible light survey telescope, can still be a strong infrared emitter and therefore readily detectable by an infrared telescope. This means that infrared observations are less sensitive to the albedo uncertainty that makes size estimates from visible light observations so imprecise. And they are capable of detecting dark objects that visible light surveys systematically undercount. NEO-Surveyor's design specifications call for it to be capable of detecting 90% of near-Earth objects 140 meters and larger within a decade of operation, which would finally achieve the congressional mandate that the George E. Brown Jr. Survey Act set in 2005, and that ground-based surveys have been unable to meet. More significantly for the story of 2026 JH2, it would substantially extend the detection horizon for objects in the smaller size ranges as well, potentially providing weeks or months of warning for objects that currently arrive with days of notice, if they are detected at all. Weeks or months of warning, rather than days, does not solve the deflection problem entirely, but it changes the nature of the problem in important ways. 8 days of warning, as we have established, leaves no realistic response options for any known deflection technology. Weeks of warning would still be insufficient for a full kinetic impact emission of the DART type, which requires months to years of lead time for spacecraft design, construction, and transit. But weeks of warning would allow for meaningful emergency planning, for public notification and potential evacuation of the most at-risk areas in the impact footprint, for the kind of coordinated international response that days of warning simply does not permit. And months of warning for a larger object in the 50 to 100 meter range that NEO-Surveyor would be capable of detecting well in advance, begins to open the window for emergency deflection options. Not a full planetary defense mission of the Apophis tracking variety, but potentially a rapid response kinetic impactor using existing launch vehicles and a pre-designed spacecraft concept that could be assembled and launched on a compressed timeline. Several space agencies, including NASA and ESA, have been developing rapid response mission concepts specifically for this scenario, mission designs that can be executed faster than a standard planetary science mission, because they sacrifice scientific instrument payload and mission flexibility for speed and simplicity. The other major development in the detection landscape is the Vera C. Rubin Observatory, a large ground-based telescope currently completing commissioning in the mountains of northern Chile. The Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, is equipped with the world's largest digital camera, a 3 billion pixel instrument capable of photographing an area of sky roughly 40 times the apparent size of the full moon in a single exposure. It is designed to survey the entire visible sky from its location every 3 to 4 nights, producing a continuous and extraordinarily detailed record of every object it can detect. The Rubin Observatory's survey program, called the Legacy Survey of Space and Time, will generate an astronomical data volume unprecedented in the history of the field, processing approximately 15 terabytes of raw image data per night, and running automated source detection and classification algorithms that will flag moving objects, transient events, and any other deviation from the static sky background. For near-Earth object detection, the Rubin Observatory represents a step change in ground-based capability. Its combination of aperture size, field of view, and survey cadence will allow it to detect objects significantly fainter than current survey telescopes, extending the detection horizon for small near-Earth objects from the ground in ways that complement the space-based infrared capability of NEO Surveyor. Together, NEO Surveyor and the Rubin Observatory represent the two most significant near-term improvements to the planetary defense detection network. Neither of them eliminates the detection problem for the smallest objects. The true Chelyabinsk-class rocks in the 10 to 20 meter range that are simply too faint to detect until they are days away under any realistic scenario with current or near-term technology. But they push the detection frontier meaningfully forward for objects in the 20 to 100 meter range, the range that includes 2026 JH2 and everything up to the Tunguska ceiling. On the deflection side, the post-DART landscape is more developed than it was before September 2022, but still sparse in terms of operational capability. The key lesson from DART, beyond the confirmation that kinetic impactors work, is that the ejector plume produced by an impact contributes substantially to the momentum transfer, and that this contribution depends on the surface properties of the asteroid in ways that vary significantly between objects. This means that deflection mission planning requires knowledge of the target asteroid's surface composition and structure, which in turn requires either prior observations of the specific object or a reconnaissance phase before the impactor arrives. For an object discovered months in advance, a two-phase mission, a small reconnaissance spacecraft, followed by the impactor, is feasible within a compressed timeline. For an object discovered weeks in advance, only the impactor is feasible, and the ejector enhancement factor must be estimated from statistical knowledge of asteroid surface properties rather than direct observation. For an object discovered days in advance, neither phase is feasible with current infrastructure. The gap between what exists and what would be needed for a comprehensive planetary defense capability against the full-size range of threatening objects is real, significant, and not going to be closed quickly. Building a standing rapid response deflection capability, maintaining a small fleet of pre-built spacecraft on standby, establishing the international coordination mechanisms that would be required to authorize and execute a deflection mission under emergency conditions. All of this requires sustained political will, sustained funding, and sustained international cooperation across decades. None of that exists today. Some of the foundations for it are being laid. The Planetary Defense Coordination Office at NASA, established in 2016, provides a coordinating function for U.S. government activities related to near-Earth object detection and mitigation. The International Asteroid Warning Network, a coordination body linking near-Earth object observation programs across multiple countries, provides a mechanism for sharing detection data and coordinating follow-up observations. The Space Mission Planning Advisory Group, an international body that advises on planetary defense mission concepts, has been developing response frameworks and mission architectures for a range of threat scenarios. These are institutional beginnings. They are meaningful. They are also, relative to the scale of the coordination problem, modest. A real planetary defense response to a significant threat would require not just coordination between scientific agencies, but decisions at the highest levels of government in multiple countries simultaneously. Authorizations for mission expenditures measured in billions of dollars on timelines measured in weeks, and technical execution under pressure that no existing infrastructure has been tested against. The honest assessment is that the planetary defense capability of 2026 is substantially better than the planetary defense capability of 2006, and substantially less than what a comprehensive response to the full spectrum of threats would require. It is a capability under construction, making real progress, funded at levels that are not commensurate with the scale of the problem it is addressing, and dependent on continued political and institutional will to remain on its current trajectory. 2026 JH2 was safe. The trajectory confirmed it. The orbital solution left no ambiguity. The rock passed through, gave us 8 days of notice, and demonstrated with quiet precision exactly where the capability currently stands and how much remains to be built. The survey continues, the construction continues, and the rocks, as they always have, keep coming on their own schedule, indifferent to the progress reports. 2026. JH2 is gone. It passed inside the Moon's orbit on a Monday evening in May, at a quarter of the distance between us and the nearest body that has kept us company for 4.5 billion years. It flew through the gap between our satellites and our Moon at 9 kilometers per second, briefly bright enough to catch in a modest telescope, briefly real in a way it had not been for the billions of years before someone in Arizona pointed an instrument at the right patch of sky on the right clear night. We knew it for 8 days. The solar system continues. The survey telescopes are running tonight on whatever mountains have clear sky above them, photographing their patches of sky and comparing exposures and flagging the dots that move. The close approach tables are updating. Somewhere in the dark, on orbits that Jupiter shaped over millions of years and that no instrument has yet caught, there are rocks we have not named, moving at their own speeds, crossing our orbit on their own schedules, briefly detectable, briefly knowable, waiting for the geometry to align and the sky to be clear and the telescope to be pointing in the right direction. Most of what passes through the dark is still unknown. That is not a frightening thought. It is simply an honest one. The universe is large. We have been watching for a long time, and we are still, in the most genuine sense, just beginning to learn what is out there. Tonight, at least, we knew this one. Thank you for spending your night drifting through the cosmos with Cosmic Drift. If these slow journeys through the science of deep space are something you want more of, subscribing means you will be here for the next one. Sleep well.